Conway's Game of Life is a very famous algorithm that falls into the category of cellular automata, or computer simulations of cell behavior. If you haven't seen my last video, I go into much detail about how the algorithm works, and I built a version of it that can run on the Game Boy Advance. The short of it is that cells, represented by pixels, can be in one of two states, alive or dead. Each generation, every cell on the screen will update based on its current state and the state of its neighboring cells. If a cell is living and has 2 or 3 living neighbors in the current generation, it will stay alive into the next generation. If it has more or less, it will be dead next generation. And if a dead cell has exactly 3 living neighbors, it will come to life in the next generation. These fairly simple rules can create a variety of complex patterns that can actually stabilize, and as long as they aren't interrupted, can exist indefinitely. The core functionality of setting an initial state of the grid, then checking every cell, applying the rules, and progressing into the next generation is identical across all cellular automata. There are a lot of small changes you could make to create entirely new cellular automata. You could change how cells check their neighbors, the number of states a cell can be in, how cells are affected by their neighbors, and the initial state of the system, without modifying that core functionality that defines cellular automata. You could even add an element of randomness, but technically it would become a probabilistic cellular automaton, but that's besides the point. I was feeling inspired to play with some of these different ways to alter Conway's Game of Life to make my own cellular automata. This video really isn't about the Game Boy Advance at all, but like an artist with a preferred medium for their art, I'm writing all of my code to run on the GBA, and all of the code will be available with the GitHub link in the description. Let's talk about randomness briefly. Randomness generated by a computer is not actually random. It is pseudo-random. There are true random number generators that measure physical things that are unpredictable, but we don't have that kind of capability on the Game Boy Advance. This means that while the numbers a computer generate might seem random, they actually can be predicted if you know how it generates numbers and what number it started with. So if a computer starts with the same random number every time, you could accidentally see the same exact simulation play out multiple times. I was careful about this by having an intro screen in which I update the pseudo-random number over 60 times a second until I hit a button. I don't know the exact second I will hit the button, so in this way, I'm adding a true element of randomness to the not actually random system. I'm using the tonk function qran, which returns a random number between 0 and 32,767, and then using the modulo operation of that number by some arbitrary value. For example, I get a random number of 24,717, and I modulo by 8. I would divide the number by 8, and then take the remainder, which will be between 0 and 7. If that value equals 0, we can call that a success. I'm going to use a lot of randomness, and most of the module values used in my cellular automata were tested and chosen to make the simulations look more interesting. You can look into these values yourself in the GitHub repository linked below, and they aren't really based on any real-world values, so just had to clear that up. When researching for my previous video, I found this other video on YouTube simulating a forest fire using Conway's Game of Life. And it's quite brief, but I liked it a lot. The behavior was really interesting, and I wanted to expand on it in my own way. From Conway's Game of Life, I used 3 states instead of 2. Green is living trees, red is burning trees, black is burnt trees. The initial state of the grid will be fully green except for 1 red cell, which is selected randomly. I will also choose a direction in which the wind is blowing. Imagine a clock with 8 directions. Pick a random value between 0 and 7, and whichever direction it lands on, I will evaluate the 3 opposite neighbors in that direction. For each green cell, we will check the neighbors indicated by the direction of the wind for red cells. For each of those red cells, there is a chance that the fire will spread to the current green cell. More red neighbors means more chances for the fire to spread. When updating fire cells, there's a random chance that they extinguish to black cells, and black cells will stop spreading the fire completely and remain black for the entirety of the simulation. And I really like this. Sometimes the fire starts on the edge of the grid and points in an unfavorable direction. Sometimes the fire is immediately extinguished, but most of the time it creates pretty cool simulations, and you can clearly see the direction of the flame and the spread of the fire. Sometimes it dominates the whole screen and grows really wildly, and other times the whole fire goes out before it does very much damage at all. And sometimes trees that are surrounded by flames avoid danger and survive. It's pretty cool. Another type of fire I want to simulate based on the game of life is a flame, like a campfire or a candle. With this one, I think the most important feature is that the fire rises upwards, so every cell will consider the 3 neighboring cells below for determining the state of the current cell. I want the cell states to indicate the temperature or intensity of the flame, white being the most intense, descending to yellow, then orange, and then red, and eventually to black with 0 intensity. And a quirk of my implementation of the game of life is that there is always a border of black cells around the screen that will never be updated as cells in the simulation, but will be considered as neighbors for the inner cells. So I can use that row on the bottom as the initial state of the simulation. I'll create a gradient from black to white to black that spans the bottom row and has a mild amount of randomness that updates every generation, independent of the cells in the simulation. For the rules of the simulation, though, I had 2 thoughts. I could use the average intensity of the cells below with some minor randomness that could alter the intensity slightly, or I could get the highest intensity of the cells below with, again, some minor randomness that could alter the intensity a bit. So I implemented them both to compare. The average rule set creates a shape of the flame I really like, and you can clearly see the intensity diminish as it rises. The high intensity rule set creates these sort of embers and sparks that I really like, and something about this one feels a little bit more lifelike. Let's keep it going with this fire theme and make a firework simulation. My initial thoughts were to start with a full black screen and create random high intensity spots over time that would spread and decay in a circular area from the center. To start, I decided to stick with one color to keep it simple, but with 16 levels of intensity. From there, I'll implement the random bright spots. When checking every cell, if it's black, give it a very, very slight chance that it could jump to max intensity. Initially, I thought I would check all 8 neighbors for each cell, but the fireworks ended up looking a bit squarish, so I decided to just check the neighbors in the cardinal directions. Now the fireworks are kind of diamondish, but I like the way they look a lot more. Now the decay should be pretty even as the fireworks spread from the center to keep the general shape, but a little randomness in the decay should add some realness like an actual firework. And finally, to add some variety in the size and the brightness, I can just vary the intensity of these random bright spots that initiate each firework. The brighter spots will have to decay more and end up being a little bit bigger. And I really like this simulation, seeing all the fireworks go off and sort of disappear into the darkness, but something feels wrong about calling them fireworks. I don't really know what I would describe them as, but firework just isn't the right term. Oh well, I still think it looks pretty cool. And there we have it. 3 cellular automata imitating 3 different types of fire. This was a really fun project to do because the game of life is such a well-known simulation, and all I had to do was make a few tweaks here and there to make them do completely different things. I did still try to give myself challenges to make the simulations more visually interesting and exciting to create, and my favorite ended up being the forest fire. Not to toot my own horn, but I was really happy with how I implemented the directional code and how effective it was in altering the simulation. You can really tell exactly where the wind is pointing without having to be told by the software at all. Let me know which simulation was your favorite and what kind of simulations you would want to try. As always, take a look at the GitHub code if you're interested. The link is in the description, and feel free to DM me on Discord if you have any questions at Startfling. And subscribe if you want. I would continue to write this code if nobody was watching, but it's a lot more fun to share with people. All right, thanks for watching.